Lecture number 4, Regenerative Vapor Power Cycle, and we will be solving some examples. Considering a regenerative cycle with one open feed water heater. Consider a regenerative vapor power cycle with one open feed water heater. Steam enter the turbine at 8 megapascal and 480 degrees centigrade and expand to 0.7 megapascal. Where some of the steam is extracted and diverted to open feed water heater at 0.7 megapascal. The rest of the steam is expanded to the uh, condenser pressure of 0.008 megapascal over here. Saturated liquid exit at the condenser. Saturated liquid exit at the open feed water heater at 0.7 megapascal. So we have got saturation vapor, saturated liquid at 0.7 megapascal over here. The isentropic efficiency of each of the turbine stage is 85%, and each of the pump operate isentropically. If the net power output of the cycle is 100 megapascal, determine the thermal efficiency, the mass flow rate of the steam entering the turbine in kilogram per hour. Um, I would be doing the same thing, like I would be not solving it fully, but I would be solving the step actually you will be following to solve this question. Uh, as I've said, like there is some assumption or there's some engineering model which we need to consider. Like each of the component as is analyzed in a steady state control volume. The control volume are already shown with a dotted line. All processes in a working fluid are internally reversible, except now that what we have done in a two-stage of turbine, and both of them were non-isentropic. The turbine, the pump, feed water heater operate adiabatically. Kinetic and potential energy of the system are negligible. And also saturated vapor exited at 4 and saturated liquid exit at open feed water heater, and also saturated liquid exit the condenser. So starting from the question itself, we will be looking for the steam table, obviously, because the working fluid is steam. Now looking at state 1, which is actually 8 megapascal and 480 degrees centigrade. So if I'm looking at the steam, which is actually the superheated steam table, at 8 megapascal and 480 degrees centigrade, let me check the steam table over here. Sorry for that. So 8 megapascal, if I'm just looking at the superheated steam table anyway, so 8 megapascal, uh, the saturation temperature is 295.06 degrees centigrade. So that means like the steam at 8 megapascal and 480 degrees centigrade is superheated. So now looking at the steam at 480 degrees centigrade and 8 megapascal, the enthalpy of the steam is 3348.4, and the entropy of the steam is 6.6586. Going back to the question, so that means like at 8 megapascal and 480 degrees centigrade, we could find the enthalpy, which is 3348.4, and entropy, which would be somewhere 6.5 something. Now, what we have to do, like expanding steam from state 1 to state number 2, where at state 2, some of the steam is bleeded out. Now, as we say, like the process is non-isentropic, and there is a thermal efficiency of, there is an isentropic efficiency of 85%. So let's for the first thing, for the first um, method, I would say, we need to consider the isentropic process. That means like as at state 2, there is none other condition given, but only the pressure is given. So considering the isentropic process, that means like we would be considering S1 is equal to S2 S now, because we do not have got the isentropic process. So S1 would be equal to S2S. Solving that S2S, we will be having the property which would be sorry, we would be having the quality which would be equal to, which would be finding out at X2S over here. So now once we have got S2S, we can find the enthalpy which would be H2S over here. So now once we have got the enthalpy H2S, we can put the we can have the formula, or we can use the formula, and isentropic efficiency is equal to H1 minus H2 divided by H1 minus H2S over here. So in this formula, the only unknown now, as we have already got the enthalpy H1, H2S enthalpy over here, enthalpy this one. So we are only left with the enthalpy H2. We have already got the isentropic efficiency, so we can solve this equation for the enthalpy H2. Once we have got enthalpy H2, then so we will be having enthalpy H2 using that formula, and obviously the method what actually I've shown you. Once we have got the enthalpy H2, please make sure like you compare this enthalpy with the enthalpy at zero, enthalpy of Hg at 0.7 megapascal. So to know that whether this enthalpy H2 is inside the vapor dome or outside the vapor dome. So by using that formula, or by using the values, I've known that the enthalpy H2 is greater than the enthalpy Hg at 0.7 megapascal. So that means like we are outside the vapor dome and we are in a superheated region. So once I'm in a superheated region, I would be using the superheated steam table now. So now at state 1, if I'm saying like I have got the enthalpy H1, at state 2, I have got the enthalpy H2 now. Now moving to state 3, finding the enthalpy H3. So there it will be a little bit tricky part, as at 3 we do not have got, again we do not have got any other values, but only the pressure is given. So finding pressure, using this pressure, we must say like we would be using the same method. That means like S2 would be equal to S3S, finding X3S, and then finding H3S over here. But there is a little bit tricky part over here, as we do not have got S2 yet. So once what I'm trying to say, like before actually going into state 3, you have to go to the steam table, and that would be superheated steam table. In a superheated steam table, you have to check the enthalpy H2 corresponding to this enthalpy and a pressure of 0.7 megapascal. You should find the entropy, which would be entropy at state 2, and that would be entropy S2. So let's check it in a steam table. For example, I've got the pressure of 0.7, and I've got the enthalpy somewhere to find out 2832.8. So using this pressure and this enthalpy, let me check like what would be the entropy. So using the superheated steam table, and superheated steam table at 0.7 megapascal over here. Let me find the enthalpy, which is 2832. So that would be somewhere over here, this one. So that means like if I'm just reducing it a little bit more, so we would be finding the entropy, which would be near to 6.880 something, or 6.81 something. So let's say yes, you would need some interpolation about it as well. So let's say Finding this using this enthalpy and using that pressure, we had find the entropy, which was equal to 6.8606. So sorry for that. So that means like using the interpolation, you can find the entropy now. So now you have got the entropy, as I said earlier now. So you have got the entropy S2. That entropy is equal to S3S, and using S3S, find the X3X, and using X3S, we will find the H3S. Now, using the same equation of the isentropic efficiency, that would be equal to H2 minus H3 divided by H2 minus H3S, and you can find the entropy and sorry enthalpy H3, and that would be enthalpy H3 would be equal to somewhere 2249. So that procedure is already given over here, so you can use this procedure as well. Now moving forward, so we have already got the enthalpy at state 1, enthalpy at state 2, enthalpy at state 3. Now the enthalpy at state 4 is straightforward, which is the enthalpy of saturated liquid at 0.008 megapascal. Now moving forward to the enthalpy H5. Enthalpy H5 would be equal to enthalpy of the work done of the pump. You can find enthalpy from the work done of the pump, which is H5 minus H4 is equal to V4 multiplied by P5 minus 4. Make sure you do not need any unit conversion. That's what that one, because this is the SI system, and we do not both of the left hand side and right hand side, they have got the same unit anyway. So you can find the enthalpy H5 from here. Considering at state 6 now, at 6, so we have got a pressure of 0.7 megapascal and saturated enthalpy at HF value of enthalpy at 0.7 would be enthalpy at state 6. Same procedure for the pump work at state number 7. We can find the enthalpy at H5, oh sorry, H7 now. Once we have got all the enthalpy, you can proceed forward to the efficiency of the Rankine cycle with open field water heater. Sorry for that. Sorry, not just directly. You can move forward to the energy balance of the feed water heater. Once you the energy balance of feed water heater would be equal to Y is equal to H6 minus H5, H2 minus H5. Now that means like you need to find the value of Y, which is actually the mass fraction, which is bleeded out at state number 2. Once you have got value of Y, work done work done of the turbine would be equal to H1 minus H2 plus 1 minus Y, H3 minus H2 minus H3, and so on. Work of the perm, Qm, and obviously the efficiency. For the mass flow rate, the total cycle work done is already given, which is 100 megawatt. So total cycle work done is work of the turbine minus work of the pump. You have already find the work of the turbine and the work of the pump. Put that value in here and you will find the mass flow rate of the steam. Moving to the next example, example 2.5, and that is example 2.5 of Al-Wakil. An ideal Rankine cycle operate with the 1000 psi absolute 1000 degree Fahrenheit steam. It has one closed feed water heater with drain cascaded backward, placed at 100 psi absolute. The condensate pressure is 1 psi. Using TTD is equal to 5 degree Fahrenheit, and the heater has a drain cooler, resulting in a drain cooler temperature difference, which is equal to 10 degree Fahrenheit. Uh, Moving to the TS diagram, or we will discuss is the schematic diagram as well. So that means like we have got a regenerative cycle with one closed feed water heater. So regenerative vapor cycle have got 1000 psi 1000 psi absolute and 1000 degree Fahrenheit temperature. It when it expanded to a second stage, and there is a feed water heater installed, and that feed water heater is installed at 100 psi. So you can imagine like it will be the second stage expansion as well, and a drain cooler pressure as well. So that means like the drain cooler, the second stage is expanded cooler, drain cooler pressure of 100 psi. Now once we have got at second stage, some of the steam is bleeded out at 100 psi, and the rest of the steam is expanded to our condenser pressure, which is equal to 1 psi. Now it's a like it has got the terminal temperature difference of TTD of 5 degree Fahrenheit and a drain cooler temperature difference of 10 degree Fahrenheit. So let me say like what is actually terminal temperature difference. So discussing like the previous schematic diagram, we have drawn the closed feed water heater as like this. So we were having at state 5 and then leaving at state 6, and the temperature at state 6 was elevated. Then there was actually a steam coming at state 2, and it was condensed and moving cascaded backward to state number 7, while there was while there was a trap or a throttle which actually pushed or which actually cascaded backward to state number 8 somewhere. So this was the whole thing. Now what is actually terminal temperature difference? So ideally the heat which is transferred from 2 to 7 should be the sorry ideally when heat is transferred from 2 to 7 should be gained by 5 to 6. So in that case, the temperature which is exiting at 7 should be equal to the temperature which is at state 6. So that means like these terminal temperature should be equal if it is 100% energy transfer. But as you can imagine, like might be some tubing installed, there might be some other stuff which actually would reduce the efficiency. So normally there is actually some temperature terminal temperature difference between them, and that is actually what over here it is being shown. So if you can imagine, them 2 points are a little bit far apart, and that's what we call it as a terminal temperature difference, and that terminal temperature difference is given as 5 degree Fahrenheit. So in other case, the temperature at 7 is a little is 5 degree greater than the temperature at zero point 0.6. This is what we call it as a temperature terminal temperature difference. Also, it's a like in this question, it's a like there is a drain cooler installed as well. So what actually the purpose of the drain cooler is, when once you exiting at 7, so you can imagine like there would be some temperature or some heat still if I'm saying like there would be some heat still inside the condensate. Now what actually the drain cooler would do, the drain cooler would install after 7 somewhere like this. It will reduce the temperature of the condensate, although it will not change the phase of the condensate, but only and only it will reduce the temperature, and the temperature of the condensate will reduce from 7 to 8 actually. Now once we have got at 8, then we can actually proceed to the throttling, and from 8 to 9 there will be a throttling, in which the pressure from 8 to 9 would reduce. Now that mean like the when we are going from 7 to 8 actually, there is a there is also a temperature, what we call it as a drain cooler temperature difference, and that mean like that drain cooler temperature difference is the temperature difference between the feed water, which is actually coming into the feed water heater, and which is actually going out of the feed water heater. So that is like the temperature difference between zero point 0.8 and the temperature difference between, oh sorry, the temperature difference between zero point 0.8 and 5. So that is actually equal to, if I'm sorry, let me check it again, that is equal to 10 degree Fahrenheit. So that there are two things given. There is actually the temperature difference between this point and this point is given, which is temperature terminal temperature difference of 10 degree, sorry, 5 degree Fahrenheit, and drain cooler temperature difference between zero point 0.8 and zero point 0.5, which is 10 degree Fahrenheit. So these are two different concepts which actually is given in this example. So now let's proceed to the question now. As there is no irreversibility in it, and the question is itself is an ideal question, ideal regenerative cycle. So that's quite easy now. So finding, let's say, what actually would be easy, we can find the at state one, we can find it easily from superheated table. Uh, Point number four can be find out also easily. Number seven can be also be find out easily. Um, yes, we can proceed further. So that means like h1 can find out be easily. uh, h1, after h1, s1 would be equal to s2, and then obviously looking for x2, and then looking for the h2. So we can find the, similarly we can find h2 over here. Moving to state 3, similar case would be there. S2 would be equal to S3, and which is also equal to S1 as well. And obviously that would give us x2, and which would give us h3 as, sorry, x3, which will give us h3. So that is okay. H4 is already there, as we said, like h7 is already there. So now going to H5, which would be the pump work. Same case which we have done. H5 minus H4 is equal to P4, P5 minus P4. Make sure there is actually, these are the English unit, so you have to proceed with the uh, multiplying with 144 divided by 778 point something to convert it like this. Uh, and then, and that is like corresponding to this one. Let's say let's move forward to that one. um, there would be actually at 6 as well, which mean like we have got at state 6 we have got a pressure of sorry, the pressure of the boiler, and that is 1000 megapascal. So at 6 we have got 1000, sorry, 1000 psi, sorry for that, 1000 psi, and the temperature, which is, we can find the temperature C6, T7 would be given. Why I'm saying it would be given, that mean like T7, sorry, T7 minus T6, T6 is equal to 5. If you go to 1000 psi, sorry, 100 psi, which is actually the drain cooler pressure, find the saturated temperature. So that saturated temperature would be the temperature at 7. So once you got the saturation temperature at 7, which is 327.82, minus that 5 from that one, and you can find the temperature T6. Once you have got T6 and you have got the pressure, go to the either compressed table, or more likely you would not be having a compressed table, but go to the saturation table, find from these two property, find the enthalpy, and that enthalpy would be using the interpolation. Now for the drain cooler, now same thing would be there. Once you have got the temperature T8, that is what actually T8 is equal to, T8 minus T5 is equal to 10. T5 is already given for, say, like Let me check it. T5 is, so T5, like in a previous example, sorry, in a previous thing, what we have said, like this enthalpy correspond to the this temperature and this pressure, which was equal to the pressure at the exit, and pressure of the exit was 1000 psi. Now T5 was 104.72, and then add with 10 of them, then you can find T8. Once you have got T8, actually go to the saturation temperature table, find from saturation temperature table corresponding to 114.72. Obviously you would need some interpolation. Find the enthalpy, which is enthalpy at H8. Now for H9, if you can imagine, what would be the H9? For a throttling process, enthalpy H8 would be equal to H9. So in a throttling process, enthalpy remain constant. Now you have got already all the enthalpy. Now you can put the values and get your desired answer. I hope you understand these questions. If you still have got any doubt in it, or you cannot solve the examples, please let me know in your Google Classroom. I would be able to answer that. Have a nice time. Allah Hafiz.